Hi everyone, welcome to this first and hopefully best session of Eurocrypt 25. I'm Emmanuel Thomé, I'm a researcher at NUIA in Nancy, and I will have the pleasure to be the session chair. And our first speaker is Nicolas Sarkis. Nicolas is a PhD student in Bordeaux in France, and he's going to be talking about differential addition on Kummer lines. Nicolas, the floor is yours.
Thank you, Emmanuel. So I'm going to talk about halving differential additions on Kummer lines. So I have a few things to define which are in the title, but first a bit of motivation. This is on arithmetic. It's based on the arithmetic of elliptic curves. So what you want to do in a elliptic curve cryptography is perform the scalar multiplication on your elliptic curve efficiently. This is what we are interested in. And also in isogeny-based cryptography, you're interested in computing chains of two isogenies. So we are interested in having efficient and finding two isogenous formulas. So this is a main motivation. So first, so this will be the outline of the talk. First, I define what is a Kummer line and talk a bit about their arithmetic, and then introduce the new half ladder. So on Kummer lines, this is first a bit of a reminder on elliptic curves. They are given by a short various stress equation, which is y squared is a polynomial of degree 3. They have this shape, and they have a group law, which you can get geometrically. And since you have a group law, one question is how do you compute efficiently n times p, so p plus p plus p. And in this work, we are interested especially in Montgomery curves, which are the second kind of curves, with y squared is x times this polynomial of degree 2. And so why are we interested in Montgomery curves? It's because Montgomery proposed 40 years ago to compute n times p, to only use the x coordinate of your base point. So you can recover x n times p with the knowledge of xp. And this is an example of a Kummer line. So you take this map from your elliptic curve to the projective line. You send the neutral element to the point at infinity, and you send an affine point, a projective point x, y, z to. You only keep its x coordinate, so x over z. And with this construction, you basically identify a point and its opposite. So every point on your projective line has two preimages, except when p is equal to minus p. That means that we have a two torsion point. So you have 4 of them on the closure, and this is the important point to define a Kummer line. And this is also how we define a Kummer line more generally. It's a degree 2 covering from an elliptic curve to a projective line, where the fibers are given by p and minus p. And the ramification points are exactly when p is equal to, the ramification points correspond to the case p equals minus p, that is the two torsion points. And this is all we need to describe a Kummer line. And also when we will consider maps of Kummer lines, we want these maps to match the ramification to be respected when you have such map between Kummer lines. So just a few examples. With the x coordinate, is the same curve as before. So the ramification points are the point at infinity. And the solutions to the right-hand side polynomial equals to 0. So you have x equals 0, which is a solution, and x equal alpha or x equal 1 over alpha, where alpha is the root of the second polynomial. Maybe not rational, but it doesn't matter. What matters is the shape of the ramification. You have this symmetry. If you switch x and z, you still have a ramification point. So this is one example. And another example is what we call a theta model. So I won't go into the details of the formulas, but the idea is that you don't need to only take the x coordinate. You can take some homographies or other maps. And what matters is the shape of the ramification. It's like the Montgomery case. You have a symmetry with xz maps to zx, but you also have a symmetry with xz maps to minus xz. So this may give you better formulas later on. So when you have a Kummer line, how do you do arithmetic with it? Because Do you still have a group law? The answer is no, because if you start from P and Q, this means you have identified P and minus P and Q and minus Q. So you do all possible combinations. And in the end, if you only know P and Q on the Kummer line, you can recover P plus Q or P minus Q on the Kummer line, but you don't know which one. So we need something else. We need differential addition formulas. And that is, if you know P, Q, and P minus Q, you can distinguish which one is P plus Q on the Kummer line. So, and we have formulas for this. Montgomery proposed this one on the Montgomery curve. You can perform the differential, as you can see, you can compute the x and z coordinate of P plus Q with P, Q, and P minus Q. And this can be achieved in 3 multiplication and 2 squares. And you also need additional doubling formulas to compute 2 times P from the data or from the x coordinate of P. And so why are we interested in this? Is we want efficient formulas. We need both formulas to do the scalar multiplication, and we want efficient formulas. And for instance, if we compare to the theta model, the differential addition on the theta model is way slower than the differential addition on the Montgomery curve, but the doubling may be faster. So you have to find kind of a trade-off for what are the best formulas, what could be the best formulas to perform this scalar multiplication. So now, how do you do that? There is an algorithm called the Montgomery ladder. It's a generalization of a fast exponentiation, but you have to deal with the fact that you're not in a group. And the idea is that at each step, you perform 1 differential addition and 1 doubling. And in the differential addition, the main idea is that at each step, does it work? No, it doesn't. Oh, yeah, okay. At each step, the difference between the 2 points is always the base point P you're trying to compute. So you always know the difference to perform your differential addition. Here the difference is P, here the difference is still P, it's P, and it's again P. So this is how we do scalar multiplication on an elliptic with the x-only coordinate. And now what we're interested in is how do we improve differential addition, how do we improve doubling? So first with doubling, this was a previous work. You have, on elliptic curves, you have 2 isogenies, that is surjective morphism with a kernel of degree 2. And what is nice with 2 isogenies, when you have a 2 isogeny, you also have its dual going from, if phi goes to E, from E to E prime, the dual goes from E prime to E, and it factors your multiplication by 2. So this is what you want to use to compute 2 times P. You want 2 isogenies to factor to have a faster doubling. And in a previous work, we explained how to find 2 isogenies formulas on Kummer lines. So now, what we want to do is, can we do something similar on the differential addition? And so we are interested in this map this time. So you map P and Q to P plus Q, P minus Q. These are the points we are interested in. It is still an isogeny, but it's not an isogeny between elliptic curves. It's an isogeny between a product of elliptic curves, so abelian surfaces. And we would like to factor it maybe in the same way as we did with the 2 isogeny, to factor the doubling. So since we're working on a product of elliptic curve, and my 2 isogeny phi is just between 2 elliptic curves, we can look at the diagonal map where you evaluate individually at P and Q to have some isogeny on your product of elliptic curves. And the question is, can you factor the differential addition maybe in that way, ideally? And the answer is, it's not as easy. You have this abelian surface A that appears, that is generic. It's not even it has no reason to be a product of elliptic curve. But you can achieve it. You can find some factored formulas. And what are those factored formulas? This is what we call half differential addition. And so yeah, if you have a 2 isogeny phi on your elliptic curve, and if you know the data, half differential addition formulas are formulas that compute P plus Q with the data of phi P, phi Q, and P minus Q. So the idea would be to reuse, when you do the doubling, you have to compute your 2 isogeny, and you want to reuse this result to also compute your differential addition. And this is what we denote half diffad. And for consistency, we also denote half double the composition with it's only the composition with the dual, but it's for consistency. So an example of half differential addition formulas, I go a bit quick on this example, but if you take the previous theta model and you look at the isogeny with this kernel, it's given by this formula, given some assumptions. And the half differential addition formulas associated to this phi are simply this one. So you can compute p plus q with only 4 multiplications, whereas the full differential addition was 3 multiplication, 4 square, and 1 multiplication by a constant. So it's faster. It's way faster, but can we take advantage of this? And the answer is yes. We have some variant of the Montgomery ladder, where in the usual one, what you do is you start from your point P, you do a full doubling, and you do a full differential addition, so you always stay on the same elliptic curve. And here the idea would be, instead, you take a chain of 2 isogenies, you go on some path of elliptic curves, and then with half differential addition and half doubling, you can go backwards and come back to the original curve. So a bit of notation. The idea is just, if you have an L-bit integers you want to multiply your base point P by, you take a chain of L 2 isogenies, you compute the pre-images P0, P1, the image of P0s and P1s and P2 with your chain. And this is the context we will work in. So you end up on some Kumar line, In practice, what we do is that we take first a 2 isogeny, and then we take the duals, then the 2 isogenies and the dual. So we alternate between an elliptic curve and its dual. And so in the Montgomery ladder, at each step, you had this differential addition and this doubling. And now in the half ladder, you would like to replace those by a half differential addition and a half doubling. So what you do first is that you start with your chain. And on the last curve, you have your neutral element and your point P4. These are the image of, by phi4 of the neutral element and the point P3. You know the difference of these two. It's the point P3. So you can apply half differential addition formulas to recompute P3 and 2 times P3. Well, 2 times P3 is obtained via doubling, but you can reuse your half differential addition formulas. Then these two are the image of P2 and 2 times P2. So the difference is P2, you still know it because you've pre-computed it, and you can, again, do half differential addition. And you can repeat it. The difference here inside parentheses is P1, and then the difference is P0, which are always your pre-computed point. And in the end, you end with 11 P0, which was the point you wanted to compute on your base curve. So to compare a bit with the Montgomery ladder, at each step, if we take, as I said earlier, the case where you take an isogeny and its dual, first, to compute your chain for each bit, you need to do an image, which is 2 squares and 1 M0. Then you need to perform 1 half differential addition, it's 4 multiplications, and finally 1 half doubling, which is an image by phi or phi tilde, so it's again 2s plus 1 M0. And if you add all of these, you end with 4 multiplication, 4 squares, and 2 M0, which is always the best case scenario of Montgomery, the basic Montgomery ladder, where so Montgomery ladder depends on the coordinate of your base point, if it has small coordinates, if it has normalized coordinates. Here, we don't have this assumption, and we are always in this best case. The issue is that it's on a theta model, so you have way more assumptions on your curves than a simple Montgomery curve. And yeah, it's without pre-computation. But since you take this chain of 2 isogenies at the beginning, you could also use a fair comparison is also to some variant of the Montgomery ladder, which uses pre-computations. So you have this Montgomery ladder from Oliveira and al., which has which does some pre-computation, and then each step it only costs 4 multiplication and 2 squares, whereas our version has a faster pre-computation, but the main step is slower by multiplication by a constant. So it depends if this constant is not too big, it's negligible in terms of time. It may be it can still be close to Montgomery ladder. And another remark is that this still holds on a Montgomery curve. Yeah, what I presented was with a theta model, so you had all this assumption with a squared and the square root being rational that I did not discuss about. You can reduce it to the case of a Montgomery curve which has full rational two torsion. So only shaped that way, and still it's not a generic Montgomery curve, but it's still way less assumption than the first one. And you have the same timings. And so now to conclude, what we used, the main ingredients was to use an isogeny in higher dimension to find formulas in dimension 1, which was the half differential addition. And the half ladder can enhance the precomputation cost, even if you lose a bit on the main step. And it's still close to Montgomery ladder in its base case scenario. And now what we try to work on is to generalize this. One great thing about this half ladder is that this generalizes well to higher dimension. As long as you have formulas that you can use as half differential addition, you could do this ladder in dimension 2, for instance, and you could use it in higher dimension to perform this scalar multiplication on abelian surfaces, for instance. And so yes, that's one work. And during the workshop in the weekend, we were looking also for a Montgomery curve with full rational two torsion and small coefficients and properties like the curve 25519 from Bernstein. And we had some small constants that I did not have time to add on these slides, unfortunately, but we managed to find some curve with good group order and good properties. So yeah, thank you for your attention.
We have time for a few questions. So I might have one. Do you have possible applications in the case of factoring for ECM when you can find a parameterization that can get away with ISO square root at some point? So certainly in the case of factoring, you would not be able to do that. So
yeah.
Yeah,
another issue you have with factoring is that you don't use in factorization, you don't use Montgomery ladder because you don't need the constant time part. So you use an algorithm called PRAC, and the issue is that the difference in your points varies quite a lot. And here with the images of your isogenies, you probably don't have the images of you probably don't know the difference.
Okay. Any other question?
Thank you for the nice talk. Do you think that it can be applied to the three-point Montgomery ladder?
I'm sorry, I'm not sure I know what is a three-point Montgomery ladder.
Like computing, instead of computing just a scalar multiplication, compute P plus K times Q.
We did not think about that. Maybe it could be generalized. You still have this issue of knowing the difference because with your isogeny images, but maybe it could be generalized. I'm not sure.
Yes, Mehdi.
So do you have a simple description of what it means for a curve to have for the Kummer line to have a fully rational theta model?
Sorry, I did not hear that.
Like, what's the condition for having a theta model which is completely rational over base field? Very simple.
It mainly was having a Montgomery curve shaped this way, and the square root of this could have to be rational. This was I had more assumptions here, so maybe you don't need the square. We had a paper also on trying to classify which curves are the Montgomery models, and we we had some simple criteria to have a theta model. Maybe you don't need the square. Yeah, I think you don't need the square. Otherwise, it's you have the square root of the a plus b, a minus b to be rational.
Okay, thank you. We'll move on to the next talk. So thanks, Nicolas, again.
Thank you.
Our next speaker is Mingjie Shen. She's a postdoc at COSIC at KU Leuven in Belgium. And her talk, I mean, you're going to be presenting your work. So. What's going on? She's going to talk about endomorphism rings. Okay, floor is yours.
Okay, thanks for the introduction. So today I'm going to talk about a joint work with Christophe Petit about computing the endomorphism ring. Sorry, let me grab this. Computing the endomorphism ring of a supersingular elliptic curve from a full-rank suborder. So here is the outline of my talk today. I will first introduce some necessary background, and then I will talk about the main problem that I'm interested in, which is to compute the endomorphism ring from a suborder. And in order to solve that, I actually solve another related problem, which is also computing endomorphism ring, but with the knowledge of some isogeny. And I will then sketch the main ideas of the paper, and finally I will talk about some applications. So we start with elliptic curves. We've seen what they are, but just a very quick recap. You can just think of them as curves defined with equations of the following form. Here are two examples given by their graphs. On the left, you have y squared equals to x cubed plus x, and on the right, you have y squared plus x cubed minus 4x. So the points on elliptic curves are just coordinates, x, y, satisfying these defining equations. So these two graphs are just to give you some intuitions, because these are graphs over the real numbers, but we will be working with finite fields of characteristic p. So what is an isogeny? Isogeny is a map sending points from one elliptic curve to another elliptic curve. Basically, you send a coordinate x, y to another coordinate x prime, y prime. For instance, here is an example of an isogeny, and there is a very important notion attached to every isogeny. It's an integer called the degree of an isogeny. To some extent, this integer measures how complicated your isogeny is to represent, to evaluate points at this isogeny. For instance, this isogeny I'm giving you here is an isogeny of degree 2. And you can see that these equations defining this isogeny, they are like polynomials of degree at most 2. So it's a notion attached to the complexity of this isogeny. Okay, then what is endomorphism? I'm interested in computing endomorphisms. An endomorphism is just a very special type of isogeny that goes from the curve back to itself. So here are some examples. If we just look at this specific curve, y squared equals to x cubed plus x, then iota sending x, y to minus x, iy, where I is the square root of -1 in your field, is an isogeny. And also pi p, which is the Frobenius map, sending x, y to x to the p, y to the p, is also an endomorphism on this curve. You can check that if x, y satisfying this equation, then these two things also satisfy the same equation. So is there anything else? Here is a simple fact and also a hint for everyone. That is, elliptic curve points form a group. So from this point of view, we can think of a class of very simple isogenies, which is you have a point, P, represented as x, y, and then you compute a scalar multiple of that point. That's just adding a bunch of the copies, the same points, and then it will land in the same curve. So that's also a very important class of endomorphisms. And we call these endomorphisms as endomorphisms to be like multiplication by a scalar. Okay, it turns out that if we consider the set of all endomorphisms, it's a very fundamental object for isogeny-based crypto. And especially the set of anamorphisms on a supersingular elliptic curve. I haven't defined the word supersingular yet, but you can take the following as a definition. So if we consider the set of anamorphisms on a supersingular elliptic curve, then it is a ring, meaning that you can multiply two anamorphisms, which is just composition of maps, and this is a rank 4 z-lattice. And this is called the anamorphism ring of a supersingular elliptic curve. So here, from now on, I will use E0 to denote this curve we've seen earlier. And we've already seen from the example that this ring contains Z, Zi, Z pi p, and Z, sorry, this is iota. Iota composed with pi p. So it's a sublattice of rank 4 that we know that is contained in the anamorphism ring. And the anamorphism ring problem is the following. If we have a supersingular elliptic curve over finite field, then we want to compute the anamorphism ring. Specifically, we want to compute a basis of this anamorphism ring as a z-lattice. And this is just a very simple example. Usually, we cannot write down such things for an average elliptic curve. OK, now let me introduce the problem I'm interested in. It's a variant of the anamorphism ring problem. You may think it's a much easier variant of the anamorphism ring problem. So basically, we have the supersingular elliptic curve, but now we also have a suborder of rank 4, whose discriminant I will denote as delta R. We already know a large chunk of the anamorphism ring, and the goal is to compute the anamorphism ring. So to give you a little more detail, a suborder is a sublattice, and it's closed under multiplication. And we are looking for an efficient algorithm. So what's the input of our algorithm? This suborder will be given by efficient representations of a lattice basis. And we will assume the representations are efficient, meaning that their size are polynomial in log of the discriminant. And this can be always achieved by doing lattice reductions. OK, so now I will give you some intuition on this problem. If we just forget about the multiplicative structure, this is just a pure lattice problem, right? So we have a target lattice, which is unknown, and we have a known sublattice inside this target lattice with an index given to us. I should have said that these lattices are of the same index, sorry, of the same rank 4 in our case. So then this index is a finite integer. OK, and there's another thing about this problem, which is there's an efficient algorithm that detects if we have a superlattice containing the known lattice R, and we can detect if L prime is contained in the target lattice L or not. You may wonder, I didn't mention such an efficient algorithm from the definition of the problem, right? But this is due to the fact that we know the elliptic curve, and also due to the recent development of an algorithm called division by an integer. I will not talk about the details, but such an algorithm exists in our case. So now the question is, how do we find L? A very naive way is to enumerate all superlattices containing R with this given index. And then you use the detecting algorithm to see which one is the correct one. But this set is very big. The size is exponential in log of the index, so that's not a very good way. A more clever way is to deal with one prime factor in the index at a time. So you list all superlattices containing R that has that specific index, which is that factor. So there are not so many of them, depending on the size of the factor you are dealing with. So then this gives you some intuition that the hardest case seems to be the case when this index contains large prime factors. And here are some known results regarding this problem. So there is a polynomial time quantum algorithm that solves a hard case, but also a very special case for this problem. So the suborder we're dealing with is of the following form. So it comes from another elliptic curve, and it's an embedding of this order, Z plus D and E0, into our anamorphism ring that we're interested in. And this capital D here is not equal to the field characteristic, and it's a prime. So for such orders, there is an algorithm that runs in quantum polynomial time. And why people were interested in such a specific order is because this was the hard problem underlying a key exchange protocol called PSIDE. So this is a summary of our main results. So basically, we follow the technique from here, but we do generalization. We just solve this problem in full generality. So given a suborder and of discriminant delta R, then we have a quantum algorithm that computes the anamorphism ring in quantum polynomial time in log of the discriminant. So that's the main result. OK, now I'm going to take a detour to another related problem, because that's how we actually solve it. So this is the isogeny to anamorphism ring problem. So the end goal is, again, computing the anamorphism ring of something, but now you are having a different extra information. So here we have an isogeny from E0, which is the curve that I defined earlier, to E, which is the curve we're interested in. There is an isogeny of degree n. And then if suppose we have the anamorphism ring of the domain curve, so now, and a weak isogeny representation of this isogeny, and we want to compute the anamorphism ring of E. By weak isogeny representation, it means we know the evaluation of phi on points up to a scalar. OK, so this problem was solved in the earlier paper from 2023, where I mentioned a hard case of the suborder under ring problem was resolved. So, sorry, I forgot to say this problem is called easy ERP, the problem I defined here. So then they started with easy ERP, and through a few reductions, they arrive at another problem called PQLP. It doesn't make any sense. I will define this later, but bear with me. Just remember this name, PQLP. And then they resolve PQLP partially, so that led to a partial resolution of easy ERP. OK, here is a summary of their result. Basically, I want to point to you what is the partial resolution that they did. So the main restriction is that the degree n is an odd integer, but does not have too many prime vectors. So O log p distinct prime vectors. Under this condition, they have a classical polynomial time algorithm that solves PQLP. So that also led to a algorithm that solves easy ERP in polynomial time under the same condition. But now this algorithm is quantum because the reduction I was showing you earlier had some quantum reduction there. OK, so how am I going to relate the problem of suborder and ring to isogeny to and ring? So that's the main ideas in our paper. So we identified two tasks, essentially. The first one is to reduce one instance of suborder and ring to an instance of the easy ERP. So then if we solve easy ERP, then we solve and suborder and ring, right? And another task is to solve the PQLP in full generality. We basically want to remove the condition on the number of prime factors. So here I want to first discuss how we solve the first task briefly. So we have a suborder R that is inside and E, and we use that suborder to define an embedding of Z plus N and E0 into that suborder, and that suborder naturally is contained in AND E. So we have an embedding from Z plus N and E0 to AND E. And then we want to find smallest such integer n. And that, again, we use the division algorithm, dividing an anamorphism by an integer that I mentioned earlier. So we first do this, and this already looks a lot like the earlier order that we were talking about, except that in that case, this n is a prime. Now we are dealing with general integers. So then the second and the rest two tasks are we show the existence of an isogeny from this embedding phi from E0 to E of degree n, and then we show how to get a weak isogeny representation of phi. I need to mention that the A1 and A2 have been done in a paper from 2022 when PSIDE, the protocol, was introduced, but only for n equal to d is a prime. So we basically our techniques are greatly inspired by those in that paper, but we are doing generalization from prime to random integers. So for the rest, I will focus on how we resolve the PQLP in full generality. Here's the statement of the problem. This might be some abstract nonsense to you at this moment, but let's relate everything to elliptic curves. So basically, this problem is saying that suppose we have the anamorphism ring of some elliptic curve given to us explicitly, and we have some integer co-prime to the field characteristic, and we have an element in the anamorphism ring, so anamorphism. And the norm is co-prime, which means the degree of the anamorphism is co-prime to the integer, and we want to find another anamorphism such that they satisfy some congruence condition, and the degree of the other anamorphism is power smooth. And this congruence condition is something like these two anamorphisms. They have the same action on E0n, where E0n is the kernel of the multiplication by n map. And they have the same action up to a scalar. So as I was saying at the beginning, degree measures how complicated your anamorphism is, but it's actually not just the length, the size of degree, but also the prime factorization of the degree. So basically, suppose we started with some anamorphism whose degree is very hard to deal with. Now the goal of this whole problem is to find another anamorphism, in some sense equivalent, whose degree is much nicer. Okay, how do we solve this problem? We again build our algorithm from the earlier paper. As I was saying, in that paper, this problem was resolved partially. How so? So the general idea, they generate nice gamma in the order, which just think of these as generating anamorphisms in the anamorphism ring. And then through some algorithm, they produce power smooth lift of sigma 0, so the initial anamorphism. And this only works when an integer, which is related to gamma and sigma 0, is a square modulo n. So, but suppose the number of prime factors of n is k, then a random number has chance 1 over 2k of being a square modulo n. So that's why they have to put the condition on n not having too many prime factors. But our intuition is this random integer is usually a square modulo half of the prime divisors of n. So we are trying to develop an iteration that doesn't give you perfect lift modulo n, but gives you some partial lifts modulo some factors of n. I guess I don't have time to go into all the details, but this is like how a sketch of how the iteration works. So we find the partial lift, and somehow we increase the lift, the modulus we are lifting a little bit, step by step, and in the end, after polynomially, at most polynomially many steps, we will be able to combine everything to give a lift for sigma 0. Okay, finally, I will quickly go into the applications. So the main applications are just to understand the relations between different hard problems in isogeny-based crypto. I want to point out one of them, which is the problem of computing one non-trivial anamorphism in the anamorphism ring. This is actually also hard. It's not even asking a full basis, but just one of them, which is not a scalar. And this problem is relevant because it underlies the security of SCI digital signature. So there are classical reductions between these hard problems. But one thing that we need to pay attention to is the query complexity of these reductions. So for instance, the reduction from end ring to one end, the query complexity is polynomial in log p. And our paper can give you a quantum version of these reductions, and this makes the reductions a lot tighter, going from poly log p into constant number of queries. I guess that's all I want to talk about. Thank you.
We only have time for a very short question. Yes, Clémence.
Thank you very much for your talk. I'm sorry if I missed it in the presentation, but can you clarify in which context you are likely to have a following suborder of the endomorphism ring you are looking for?
I think the initial motivation was from the key exchange protocol, but it was already broken, and our paper can be thought of a generalization of the problem, and I don't have another protocol in mind that actually gives you a full rank suborder. more from the theoretical point of view, I'm interested in this problem.
Okay, thank you. Thanks, Minji, again. Okay, our next speaker is Antonin Leroux. Antonin is a researcher at DGA in Rennes, in France. And Antonin, the floor is yours.
Okay, thank you very much for the introduction. So yes, so today I'm going to present to you a new post-quantum verifiable unpredictable function, or VUF, which leads to the following two very interesting applications. First, we get from there the most compact post-quantum verifiable random function scheme in the random oracle with the fastest implementation of a post-quantum VUF scheme. And also the first hash-and-sign isogeny-based signature scheme in the standard model. Okay, so first a quick introduction on verifiable functions. So the algorithmic description is pretty simple. You have three algorithms. The first one takes a set of parameters and outputs a public key and a secret key. Then you have an evaluation algorithm that takes a secret key and some input and provides an output and a proof. And finally, we have a verification that takes the public key, the proof, the output, and the input, and checks whether this is valid or not. So the basic security properties we require from that are first correctness, which means that if we execute all these algorithms in an honest manner, the final output will be 1. Also, we need that this is really a function, which means that for every input, there is only one output that passes the verification. And also, we need that for cryptographic purpose, we need that the function needs to be hard to evaluate without, so this is a typo, it's without the secret key. And we have actually two flavors of that: unpredictability, which is just mean that the output is hard to compute. So this is the computational variant, and this gives you a VUF. And the stronger variant, decisional one, of pseudo-randomness, which means that the output is indistinguishable from random. And that's how you get a VRF. And in most cases, I guess, the stronger one is the VRF, which is why in most applications we're interested in this one. But actually, in the random oracle model, it's pretty easy to go from a VUF to a VRF. That's a classical transformation from a decisional computational problem to a decisional problem. Usually, you just use a hash function at the end, and it gives you what you want. And so in the random oracle model, VUF implies VRF, which is why it's a physics to construct a VUF. To understand a little bit about the obstacles to build such a thing, I think you can see this construction in two ways. First, you can look at it as a verifiable, unpredictable function. Unpredictable functions are pretty easy to come by, but the hard part here is really to verify that the output was correctly computed. Another way is to see it as a unique signature. VUF and unique signatures are essentially equivalent once you restrict the message space. And here, the unicity part is the hard one. Otherwise, like if you have a unique signature, then you essentially have a VUF. But it turns out that most signature schemes that we know, especially in the quantum setting, do not have this uniqueness property. For instance, you can rule out all signature based on sigma protocols. So for instance, in the case of isogenies, this means you can forget about anything related to ski sign. And also this means that actually lattices are a poor tool to build this, because usually due to the noise that they use, it's quite hard to get this uniqueness property. Okay. So now a little bit of background. Thanks to Mingjae, I can go quite quickly here. So we start again from elliptic curve. Isogenies are simply rational maps between my curves. So just think about polynomials. And there is this notion of size, which is the degree, that gives me roughly the degree of these polynomials that I use. And so if the degree is big, then my polynomials are going to be big, and that may be a problem. An endomorphism is simply an isogeny from a curve to itself. If we look at the set of endomorphisms, we get a ring which has finite characteristic either dimension 2 or 4. In isogeny-based crypto, we look at supersingular curves, which are the curves whose endomorphism ring is dimension 4 object living in this quaternion algebra, which for the purpose of this talk you can just think about like a 4-dimensional vector space, which means that all the objects that we are going to be interested in can be represented by dimension 4 vector or matrices. And the hard problem underlying most of isogeny-based crypto is this problem of computing the endomorphism ring from the curve. We have this tool that is called the Daring correspondence. So the first step of this correspondence is actually this equivalence between elliptic curves and their endomorphism ring, but you can actually extend that to different objects, which I'm not going to define because it's not going to be very important to follow my talk. Just know that there is really this dictionary and you can go from one side to the other and everything is well defined. And the only thing you need to remember essentially is that for isogenies, the equivalent are called ideals. And the nice thing is that thanks to this, the fact that the quaternion algebra is a vector space, we have essentially a lot of efficient operation in this quaternion world. So this is going to be used as a constructive tool. Now, to get the high principle of the construction, I want to use this abstraction of isogeny representation, which is going to be quite useful. Indeed, it's pretty natural to mean what does it mean to compute an isogeny, and from the definitions that I gave, you may say, okay, well, it's obviously when I want to compute it are these polynomials that I introduced. The thing is that, as I said earlier, this is not always very efficient. And in crypto, we use big things. And in that case, well, you may end up with a polynomial that you won't never be able to write. So the solution that we have usually is to take a degree that is smooth, because in that case, you can factor the isogeny and reduce your computation to a bunch of small polynomials, which can be represented efficiently. Okay, but this is not satisfactory in general, and this is why we can use this abstraction of an isogeny representation, which is just some data related to some unique isogeny, such that there is some algorithm in which I can give the data and some point, and it will evaluate the isogeny on the point. And that's essentially the only thing I really need to do from an isogeny, evaluate it. And I said that this representation is efficient when first the data is pretty compact and also the algorithm runs efficiently. Okay, so now what kind of representation can we have? Well, we have the one that I've already introduced, and as I said to you, it's not always efficient. Then we can use the kernel of the isogeny. So the kernel is just the set of points that are sent to 0 by the isogeny. And so this is just a bunch of points of the domain curve. And since isogeny, elliptic curves are like at worst 2-dimensional objects, this means that I can give at most 2 points, and it will define uniquely my kernel. And since there is a one-to-one correspondence between the kernels and the isogenies, then this is actually a valid representation. And it's pretty compact because, well, sometimes I can just give 1 or 2 points, which is way better than 2 to the 100-degree polynomial, for instance. The thing is that it's not really efficient because the only way we have to evaluate the isogeny from there is first to compute the polynomial and then use it for the evaluation. So it's a little bit better in some cases, but it still does not solve the problem. Then we have this ideal representation that comes from the Daring correspondence that I mentioned already, and this one is actually efficient because as I said to you, in the quaternion world, we can do everything efficiently. So that's pretty nice. And actually, we have another example of an efficient representation, which comes from these attacks against SIDH that appeared now a few years ago. And it turns out that if you evaluate your isogeny on a few well-chosen points, then you have an efficient algorithm to actually compute the isogeny and evaluate it on every other point. And that gives us another example of an efficient representation. So if I give a quick summary, I can give you this table, which I'm not going to comment in full detail, just a few words on it. So first, the color code. When it's orange, it means that it can be efficient when the degree is well chosen, in particular when it is smooth, but in general it is not efficient. When the color is blue, it means that most of the time it can be made to be efficient, but not always. When it's green, it means that it is always efficient. Finally, I want to add a few comments on the on two columns. This required knowledge column first, because essentially some of these representations require more knowledge than others. And in particular, the ideal representations require to be able to go from the world of elliptic curves to the world of quaternions, which implies that we actually know the endomorphism ring of the curve. And of course, this is a highly non-trivial information to get. And so this representation actually assumes a strong knowledge, which is not the case of the other ones. But of course, this strong knowledge allows us to do powerful things. So there is something to be gained here. Also, I want to talk a little bit about the last column, which is the one about sampling efficiency. By that, I mean, like, if I give you a curve and some degree, how easy is it for you to get like a representation of any isogeny of degree n? And in most of the case, it's not so easy. And one of the nice things about this kernel representation is that actually you can just sample points from your curves, and then you get one representation of your isogenies. So this feature is going to be useful for us, so I just wanted to highlight it. And I guess the generic conclusion of this slide and all of this section about isogeny representation is that in the generic case, and the worst case is actually when n is prime, all these representations are really not equivalent to one another from an algorithmic point of view. And this is what we are going to try to exploit to build this VUF construction. And the best case for us is going to be n prime, so this is what I'm going to use for the rest of the talk. Okay, so now I can get to give the intuition about the construction. And I'll just go step by step to give you a high-level idea of how this might work. So my first step is to have something which will act as my keys, public keys and secret keys. And the main thing I require from my secret keys to be hard to recover. So what I can take is the usual thing we actually do in isogeny-based cryptography. My public key will be some curve, and my secret key, the endomorphism ring of that curve. Then there is the input to my function. And this one needs to be easy to sample from the public key, so from the curve. And if you remember the thing I said about isogeny representation, the sampling part is actually very nice for the kernel representation. So this is what I'm going to use. I'm going to find a way to take my x that lives in some input space, and so I have some function h that takes the curve, the x, and give me a point of order n, and this will give a kernel representation for one isogeny of degree n. Then there is the output of my function, and this one needs to be hard to compute without the secret key. And well, it's pretty nice because it turns out that from my kernel representation, in general, I don't have an efficient algorithm to evaluate my isogeny. So this is when my output is going to be the evaluation of the isogeny on the curve. So this means I just take the codomain of the curve, and this one is supposedly hard to compute from the kernel representation. And finally, to complete my construction, I need something to prove that the thing was constructed efficiently. And this, of course, needs to be easy to verify from the knowledge of the public key only. So what I would like to have is an efficient representation that does not require my secret key. And this is exactly what is given to me by the HG representation. So my proof is going to be given by this HG representation. And finally, this ideal representation, which is the main tool, that requires the secret key. I'm going to use that to actually compute the HG representation and the output of the function. And since everything is efficient with that one, then I'll be able to complete the protocol. The main algorithmic challenge for this is this task of using the ideal representation to compute my proof. And this is done with an algorithm that is called ideal to isogeny, which was introduced in the SkiSign 2D West paper in 2024, and that is now also used in the round 2 submission of the SkiSign signature. Security-wise, so I talked about key recovery. This is based on the endomorphism problem. So here I'm relying on a very standard problem for isogeny-based cryptography. If I look at, in particular, the pseudo-randomness and the unpredictability, in fact, of my VUF, I have something which is more ad hoc. So if I introduce this oracle that just takes a curve, a point, and outputs a valid representation for the isogeny associated to that point, then the problem I rely on is this one more isogeny problem where I'm given access to the oracle a bunch of times, and then I need to produce a new valid compute, a new valid codomain of an isogeny which was not given as the output of the function. So this is a non-standard problem for cryptography. It has been studied in the context of isogeny-based cryptography because it underlies the efficiency of some of the schemes, but it was not used in itself as a cryptographic problem. So, as I said to you, I have two applications from this VUF. The first one is a post-quantum VRF, which, as you can see from the numbers here, is very much more compact than existing constructions. It doesn't have any restriction on the number of evaluation, which is not the case of all post-quantum VRF. Also, the uniqueness is actually unconditional, whereas in most cases, it's only computational. And I made a proof of concept C implementation of this protocol based on the code of SkiSign. This is not fully optimized. This was run on a generic laptop. It's just to give you some idea of how long it might take. I think with a careful implementation, you should gain something like a factor 3 maybe in these numbers. And it turns out that most of this construction in the table have not been implemented. So it turns out that, as far as I know, this is the fastest implementation of a post-quantum VRF scheme. I'm not claiming it's the fastest ever and it cannot be beaten, but as far as I know, yeah, it's the fastest existing one. And yeah, just maybe I can point out that if you look at other constructions, in particular those based on lattices, you may notice that there is a huge gap, like the huge gap in the sizes. And the gap is much wider than if you look at signatures, for instance. And the thing is, like, we can build a VUF or a VRF almost as efficiently as a signature from isogenies, whereas if you use lattices, you're much less efficient in building a VRF than building signatures. So the gap is much wider here, and this means isogenies may be actually a very promising candidate here for this type of construction. The second application I have from this VUF is an hash and sign signature. So the comparison with SkiSign is that the performances are essentially more or less equivalent, meaning that they are within a factor 2 because it is using the main building blocks. And so the signing is a little bit faster, evaluation is a bit slower, and the signature is a bit bigger. All that to say that in itself, I don't think this signature is that interesting, and I'm not saying we should replace SkiSign with it. Just that the principle of this construction is very different. So it might open new possibilities for isogeny-based cryptography. Quick conclusion. For future work, we need more analysis of this new problem, and in particular in the quantum setting, because it was used as a constructive tool before, so most algorithms are in the classical setting. And then the question is, can we build more constructions from this framework? And if there is one takeaway from this talk, is that maybe this VUF, VRF type of construction might be one of the most promising applications for isogeny-based cryptography. Thank you.
Thanks for your talk. Questions, Boyan?
Sorry about possibly a stupid question, but when you said maybe it's 3 times faster, hopefully, with that C implementation, I'm wondering how you got that number, because typically, if you optimize it, it can often get like 10 times faster. So how
it's because here the concrete optimization I have in mind is really the optimization of the finite field arithmetic, which is the part which is not optimized in my proof of concept implementation. And we have some experience optimizing this type of finite field arithmetic from SkiSign. And this is where I get my factor 3, because I feel like this is what we should get, possibly.
Thank you, and thank you for the fine talk.
Thank you for the talk. And with these optimizations, do you think that you could somehow get competitive against SkiSign or not?
Yeah, probably. The numbers I said here are not extrapolated from the. When I say the time is within a factor 2, it's not extrapolated from my implementation, but just when you look at the operations you need to do, it looks like you have like a little less than twice less operations for signing, a little more than twice more operations for evaluations. And the reason why I don't have a fully optimized implementation is because the characteristic is a little bit different. So it's not the same one, so we can't use the same exactly the same thing. But it's a prime with roughly the same shape, with a big power of 2 dividing p-1. So probably we can use most of the same optimizations. Yeah. So this would have faster signing than SkiSign, I think, and slightly less fast evaluation.
Okay. Any more question? Maybe. Yes, one.
Apologies for the voice. You mentioned that there's a reduction from VUF to VRF in the random oracle model. Do you have any comments about it in the quantum random oracle model? Thank you.
This is a good question. To be honest, I've not looked at it very carefully, because this, like, you can study this transformation from a very theoretical crypto point of view, and I'm not a TCC guy, so I don't know, but yeah, I don't really know. But to be honest, I don't think it should be that difficult, because I think like the main problem usually with QROM is like when you use rewinding and this type of stuff, and I don't think the reduction from VUF to VRF requires this type of stuff, but I'm not an expert, so.
Okay, thanks for your questions. Thanks for your talk. And we'll move on to a track switch break, and next session